Back in 2017, a team of researchers at Google dropped a paper with a surprisingly simple title, Attention is All You Need. But don't let the name fool you. This wasn't just another research paper, it was a seismic event, an earthquake that would completely reshape the world of artificial intelligence as we knew it.
So, to really get why this paper was such a lightning strike, we have to go back to a really fundamental problem. For years, AI models learned language pretty much the same way we do, one word at a time. But this created a massive bottleneck. I mean, how can a machine really understand the deep meaning of a long, complicated sentence if it's only ever looking at one tiny piece at a time?
And this problem had a name, the sequential bottleneck. It was the one major roadblock that was holding AI back, preventing it from truly understanding the massive, complex world of human language.
Before this paper came along, the undisputed champions of language processing were what we call recurrent neural networks, or RNNs. And the idea behind them makes a lot of sense, right? The network reads the first word, holds it in a kind of short-term memory, then reads the second word while thinking about the first, and just keeps going like that all the way down the line.
But this one-word-at-a-time process had a couple of fatal flaws. First, if you fed an RNN a really long paragraph, by the time it got to the end, it had pretty much forgotten what the beginning was all about. And second, because it was strictly sequential, you couldn't use all the crazy parallel computing power we have today. It was just fundamentally slow and incredibly hard to scale up.
This slide just lays out the difference perfectly. On the left, you have RNNs, which were like playing a game of telephone. The message takes forever to get to the end, and it gets all distorted along the way. But on the right, self-attention, well, that's like putting everyone on a giant conference call. Every single word can hear every other word instantly, all at the same time. The process goes from taking as many steps as there are words to just one.
And that brings us to the breakthrough. The authors of this paper made a really radical proposal. They said, let's just throw out that whole sequential method, get rid of it completely, and bet everything on this new parallel approach.
I mean, just listen to this quote right from the paper's abstract. This was a declaration of war on the old way of thinking, dispensing with recurrence entirely. They didn't just want to improve the old models, they wanted to replace them. And they called their new creation the transformer.
So what's the secret sauce inside the transformer? It's a mechanism called self-attention. Here's the best way to think about it. For any single word, the model calculates an attention score for every other word in the sentence. That score basically tells it how much focus to put on those other words to understand the current one. And the incredible part? It does this for every word all at once.
So how does this whole transformer thing actually work? All right, let's pop the hood and take a look inside.
Okay, so this is the famous diagram of the transformer from the paper. I know, it looks a little complicated, but it really just boils down to two main parts. Over here on the left, you've got the encoder. Its only job is to read the sentence you give it and build a rich numerical understanding of what it means. Then, on the right, you have the decoder. It takes that numerical meaning and uses it to start generating the new output sentence.
We can simplify the whole process into 4 key steps. First, the words you type in are converted into vectors, basically numbers, that also contain information about where they are in the sentence. Second, the encoder processes all of these words in parallel to get the full context. Third, the decoder gets to work and starts generating the output. And finally, a layer at the very end looks at what the decoder did and calculates the probability for what the next word should be.
But the researchers didn't stop with just one simple attention mechanism. Oh no, they supercharged it with something called multi-head attention. You can see it on the right. It's basically like having a bunch of different attention processes all looking at the same text at the same time. You can imagine one head is focusing on grammar, while another is looking for thematic links between words that are far apart. It creates a much richer, way more nuanced understanding of the text.
But hang on a second. If everything is being processed at once, how in the world does the model know the order of the words? Well, this is where the authors used a really brilliant trick called positional encodings. They created this unique mathematical signal. Think of it like a digital fingerprint for each position in the sentence. That signal gets added to each word's data, which gives the model that crucial sense of sequence without ever slowing it down.
Okay, so the theory was beautiful, it was elegant, but the real question is, did it actually work? And the answer was a loud, resounding yes.
Take a look at this table from the paper. It shows the results on a standard translation test.
Now, this blue score is just a way to measure translation quality. Higher is better. You can see the previous top models were getting stuck around a score of 26. The new transformer model, it didn't just beat them, it jumped all the way up to 28.4. And it did it using just a fraction of the computational power.
Now, I really need to put that into perspective for you. A 2-point jump on this specific benchmark was, well, it was astronomical. That's the kind of leap forward in a field that you might see once in a decade. It was definitive proof that this new architecture wasn't just better, it was in a whole different league.
And it achieved this with staggering efficiency. The transformer got this new state-of-the-art result using less than 13% of the computing resources of the next best model. This efficiency, this massive improvement, is what finally unlocked the ability to train the enormous models that we all use today.
So, these results, they didn't just set a new record. They kicked off a revolution, and they built the very foundation for the AI world that we live in right now.
I mean, this timeline really tells the whole story. Just 1 year after this paper was published, Google released BERT, which was built using the Transformers encoder. A year after that, OpenAI released GPT-2, built on the Transformers decoder. And from that moment on, the Transformer became the undisputed blueprint for almost every single major AI model that followed. So why does this one paper from 2017 still matter so much today? It's because it solved the fundamental scaling problem. By making parallel processing possible, it unlocked the ability to train models on datasets the size of the entire internet. Every time you use a modern chatbot, a translation app, or even an AI image generator, you're interacting with a direct descendant of the ideas born in this very paper.
The transformer was the perfect answer to the biggest problem of its time. It absolutely shattered the sequential bottleneck. And that leaves us with a really compelling final question to think about. What is the next bottleneck that AI needs to break?
This is for entertainment purposes only.